Okay, I'm going to go ahead and introduce you, Qingyao. Because this is an unusual time, we're expecting that remote attendance will be a little lower than normal. But good morning or evening to everyone. Welcome to the latest edition of the CIIR talks. Today's speaker, so it's 10:30 in the morning here, which is an unusual time. It's 10:30 at night in China, where our speaker Qingyao is coming from. So Qingyao got his bachelor's degree from Tsinghua University, and then he came here to UMass, where he got his master's degree and PhD working under Bruce Croft, got the PhD in 2019. He then went off to the University of Utah, where he was on the faculty for 3 or 4 years, and then the call of the alma mater beckoned, and he went back to Tsinghua University, where he is now an associate professor in the Information Retrieval Lab, CIIR, although is that how you guys pronounce it, CIIR? Or is it TUR?
Well, we usually just call it THUIR.
It's like the IIR.
Yeah.
We don't have it's not CIIR, it's, okay. But it's the IR,
yeah.
basically there. So he has a strong service record in the field. He was the general chair of CIIR AP, that's the Asian Pacific edition of CIIR in 2023. He served as the program chair of NTCIR. He served as an associate editor of ACM TOEIS. And an area chair or senior PC member of a lot of the major conferences, if not all of the major conferences in the field. He's received a lot of awards. For example, he received the CIIR Early Career Researcher, the ECR award, which is fairly new. And so he's one of the very first or second classes of people there. He got a Best Paper Award last year from CIIR, which is great. He also got a Best Paper Award in CIIR Asian Pacific 2023 when he was general chair. Nothing suspicious about that, right? Actually, that was a Best Paper Honorable Mention, I think. He's had a Google Research Scholar Award and so on and so forth. So he's got several awards like that. His research interests continue to be in information retrieval, not surprisingly, given what's going on in the world, with some focus on the intersection between information retrieval and generative AI. He's interested in how you can use these things to build better systems, to improve ranking, and in particular, to deal with retrieval augmented generation. So in that context, he's going to talk to us today about, let me see if I can get this right. Oh, actually, you should share your screen now, about dynamic and parametric.
Oh, yeah, sure.
Yeah, dynamic and parametric RAG, retrieval augmented generation. So when his screen is up here. Oops. Okay, we're getting feedback. So before I ask you to clap for him, I'll just say, if Qingyao is happy to be interrupted if you have a question. If you're remote, raise your hand and we'll get a little notification on the screen. If you're local, you're going to have to speak up, and then we'll have to give you the mic, because that's the only way he can hear you. The microphone system in the room is not working properly, so we'll use the mic if you need it. So just speak up and you can interrupt him. And you can interrupt him. He's also going to pause periodically for questions if it works better. So anyway, everybody, please join me in welcoming Qingyao to the CIIR talk. Thank you.
Yeah, thank you so much for the introduction. And thank you so much for inviting me. It's good to be back virtually. Hope I can be back physically next time. Yeah. So the title of my talk is Dynamic and Parametric Retrieval Augmented Generation. So obviously I'm working on retrieval augmented generation. And so I will just go ahead. Just a little bit background. So we know that we are in an area of large language model because, well, large language model is everywhere right now. It's probably the most popular app and model in the past like 40 or 60 years. We see that ChatGPT has rise in just, well, get about 100 million users in just 2 months. And recently DeepSeek has get 100 million users just in 1 week. Well, it's crazily hot, right? There are many good things about large language model that we always want, especially as an IR researcher, there are features like natural user interface. Chatting with large language model is more natural than just putting keywords in the search box, right? And also, large language model can help us, and it has a very strong understanding and reasoning ability to deal with text data and even not text data. And it has very strong task generalizability. This is the thing we really want. We want a model that can deal with any type of information need or any type of information task. And large language model apparently have very strong power in this area. So, and because of this, there are questions like, well, I just captured this screenshot from a website, just talk about news, whether ChatGPT will replace search engine because large language model is so powerful and many people are using it to answer their questions. So there are opinions and thoughts thinking that large language model may replace traditional search engine in the future. Well, some people think that, but I'm not one of those guys because we know that large language model have many problems that cannot be solved without search engine and information retrieval system. For example, the most well-known problem of large language model is, well, hallucination, because large language model are designed to to be able to generate new stuff and to create stuff. It naturally has things like hallucination, and it also, when it generates a response or provide an answer, it may not be that easy to trace back to what exactly the source of that information comes from. And other than those problems, another very important problems of large language model, at least for information retrieval tasks, is that it lacks flexibility. We know that training a large language model takes like millions of dollars. Like the Gemini 1 took, this is a figure I find online. It says that Gemini 1 took about 200 million to build, which is crazy. Well, although there are some cheaper model to build, but most of them are still very expensive. And whenever we have new information come, or we want to update the old information, the only way we can do it with large language model right now is to retrain it, like change the training data and retrain it, hope it can forget what the old data is, and hope it can memorize the new information, which is very, very expensive and very, very difficult. So because of those problems of large language model, a very popular and effective way to solve this problem is, well, retrieval augmented generation. And I think everyone in the room are very familiar with retrieval right now. And I just give a very quick description about this part. Basically, retrieval augmented generation is to use the power of retrieval system to retrieve information and use that information to help large language model generated maybe more grounded or more reliable output for users' questions, users' tasks, etc. If we want to make this whole process more formal, we can have this figure. Basically, we have a lot of information, a collection of documents, or just a corpus. We put it into a retrieval system, and given a specific user input, we can retrieve some relevant documents. That's what IR systems are very good at. Then we just put those documents into the prompt of large language model together with the user input, and hope the large language model could follow our instructions to generate the final response based on both the user input and the retrieve the document. And in many cases, this pipeline works pretty well. It can help us solve the hallucination problem quite effectively. And in this pipeline, there are a couple of things that are quite important. For example, the first question is, to ask the retrieval system to retrieve document. So we can either put our user input directly to large language model to get an answer, or we can ask the retrieval system, get the document, and then let large language model do the task. If we are doing a naive RAG pipeline, probably we will just do retrieval anytime. And recently, we have seen a lot of work on so-called deep search system. Basically, they just train large language model to learn how to use retriever as a tool so that they can search for information online when they need it. In that way, we just teach our large language model to know when to ask questions, when to ask the retrieval system. Another part of this RAG pipeline as a knowledge injection pipeline is what to ask. Apparently, when you try to use a retrieval system, you need to first know what exactly you want to ask, or what exactly the query you want to submit it to the retrieval system. And in some naive RAG pipeline, people just use the raw user input as the query to issue it into some retrieval system to get the document. And that type of paradigm works in some times, but it may not be that good in some other times because the user input are not designed for a retrieval system in many cases. So there are other type of more fancier, much fancier pipelines like deep search. They will do agentic framework like prompt LLM to ask questions to retrieval system to get the information they want. Basically, we just use user input or let the LLM decide what exactly we want to ask into the retrieval system in this RAG process. And the last part is how to use the information we get from retrieval system. The naive pipeline would just put all document into the prompt, and the so-called deep search pipeline would do this in a better way. They might build a reasoning path and do this like multiple step retrieval and generation. As in the end, they just put document into the prompt to generate the next question or the final answer. So if we look at the way we solve those three problems, we can see that actually in this whole process, we just treat the large language model as a black box. Basically, we just treat it as a static black box and we do all the tricks through prompts. But if we can dive into large language model, well, apparently we have, if we use open source model, we can actually see the parameters there. Is it possible for us to build better RAG framework in this way, to build better RAG framework that can better solve those problems? There are many advantages if we can do this type of dynamic RAG in this process. For example, if we can see the actual parameters of large language model and the actual state of large language model during generation, we can detect when it will going to hallucinate and choose the time we want to call or use retrieval system in this process. We have done a couple of work on this, and there are also a lot of relevant paper on this part. Other than when to ask, there are also the question of what exactly to ask. So if we can see inside the large language model, we can check about it, probably its internal state, to find what exactly is needed for the next generation or what exactly is needed for the final answer. Then we can generate a query or other type of things that can help us retrieve the relevant document based on the large language model's internal state. We have done a couple of work on this, and there are still many open questions on this direction. And what we are going to talk, what I'm going to talk about in today's talk for most of the part is the last question: how to use the retrieved knowledge, how to use the retrieved information for large language model based on its internal parameter or internal state. If we can put the retrieved document directly into the large language model, it perhaps can help it better use the information contained in the document to generate better response. And other than that, we have other advantage, and that's what we are going to talk about in the next couple of slides. So in today's part, today's talk, I will mainly focusing on two of our recent work on this direction. The first one is decoupling retrieval and generation, and the second part is parametric RAG. Okay, so let's go ahead. The first part, decoupling retrieval and generation. So we all know that the naive RAG pipeline or the vanilla RAG pipeline we just use in-context learning for knowledge injection. Basically, it means that when we retrieve some document, we just put it into a predefined instruction template, and then put all the questions and documents into the prompts, ask a large language model to generate the final answer directly. That is a typical RAG pipeline we have. But there are a couple of problems with this type of pipelines. The first problem is related to the input context. Obviously, if we put a lot of documents into the context length will increase, right? Especially when we consider documents that are pretty long, like web page. Although there are some way to split the long document into short document, but in the end, if we put a lot of document in the prompt, it will still increase the context. And long context lead to a lot of problems like higher inference costs and longer response time. Another problem is like when we do RAG, we basically put the document into the input prompt of the large language model. And whenever the large language model need new information, we have to stop it and redo this retrieval and, well, prompting stuff. And the reason why this is not good is because right now we are working on some models like reasoning model. It usually generated a very long reasoning chain to generate the final answer. But whenever it needs information, if you just stop the reasoning and put the document in and redo the generation and redo the reasoning, it will break the reasoning path. And in many cases, it could actually make first, it will be much slower because you break the long reasoning path. And the other problem is related to the effectiveness parts. So there are two problems in the effectiveness parts. One is information loss. If we put too many things in the context, there are many problems with this long context input, like some important information may lost in the middle. And also there are many studies showing that if you put document in different sequence into the large language model, they may produce different answer. Like this is the problem of permutation sensitivity. It's not a good thing because in the end, we want the model to have reliable and usually kind of like a fixed response based on the fixed input data. We don't want it to generate it randomly, right? And another problem related to what I just mentioned is like, if we frequently do this type of retrieval, generate, then interrupt it, and then do retrieval generated process, it will make the internal reasoning path of large language model less reliable because you always break it. And also another problem is like, if you use this type of way, you will see that after maybe one round or two rounds, the instruction following ability of that model would drop, mainly because you have cut it for too many times, and also you have put too many things into the context. For example, we have a figure here. In this figure, you can see that for a vanilla RAG pipeline, if you put too many documents into it, the performance of it dropped very quickly. The performance of putting 20 documents is much, much worse than the performance of putting just 3 documents into it. Okay, so these are the problems of doing this vanilla RAG in context learning. So how do we solve it? So the question is, can we decouple this retrieval knowledge from the input context and do RAG on the fly? If we can decouple the retrieval and the retrieval knowledge from the input context, we can avoid many of those above problems in this process. So that's the goal of our work in this direction. We want to decouple the retrieval knowledge from the input prompts. So we don't want to put the retrieval document directly into prompt to do this RAG. We want to find other way to do this. But how? So there are a couple of ways, and in this paper, we're focusing on one way, that is to use cross-attention mechanism. Well, this figure is a little bit heavy, I know, but I will go through this figure part by part to make it clear. So in this process, the first part we want to do is to do knowledge encoding. We want to put the document we retrieve into the large language model, and we don't want to put it into the input prompt directly. In that, to do so, we have to first encode our retrieved document into some kind of internal representation for the large language model. So here we build a module to pre-encode the external knowledge into the KV cache of large language model. There are a couple of things I want to note in this process. First, the KV cache we generated through this process must use the downstream large language model we want to use. We don't need to train it, but we must use the same large language model for this encoding and the downstream generation. Otherwise, the language model cannot understand what exactly it is, what exactly the information is in this KV cache. And another thing we want to do in this external knowledge encoding process is that we want to do it without query. That is to say, we want to do it offline. We can encode each document separately into KV cache so that in the online inference process, we can just retrieve the KV cache directly and put it into large language model. So this is the knowledge encoding part. The second part is the knowledge aggregation, which is the most important part. We want to do this knowledge aggregation without prompt. So if we don't want to do that in prompt, we have to put the knowledge or put the retrieval document into the model into the internals part of the model, right? The way we do this is to use the attention layer of the model. Basically, for the original large language model, it can do, for example, if we input a query here, it can do self-attention operations to do all the encoding, all the interaction to generate the information there. And right now, given our retrieved document, the retrieved KV cache of the document, we want to use those documents to guide the generation process of the large language model. So we build a cross-attention operation layer. Basically, it put the KV cache alongside with the the internal like KV of the large language model, and use a small portion of trainable parameters to put the to convert KV cache into some kind of internal parameter that can be understood by the large language model, so it can do this cross-attention operators, cross-attention action or operation on our document in this way. Okay, so that's basically it. So this is the way we want to decouple retrieval knowledge and the input prompt with large language model. Because we do this cross-attention operation, we don't need to put the document into the initial prompt of the large language model. And also we can remove the document during the inference process of the large language model without interrupt its generation. There are a couple of advantages of this decoupled RAG. For example, it can do offline document encoding. We don't need to do all the document encoding online. And also because it do document encoding separately for each document, we can do this parallel document encoding. And more importantly, because the document encoding are done in a separate way, the model itself can be permutation independent. And we naturally separate the documents from the input instruction. So the model has better ability to follow the instruction of the user. And here are some experiments. We did a couple of experiments on a couple of question answering dataset and slot filling dataset, and also some dialogue dataset. We tested on Llama, and we compare our model with some naive RAG baseline with fine tuning for each text. We just use the naive RAG pipeline and use the same data we use to train our decoupled RAG to train those RAG pipeline to see whether our method can beat their RAG fine-tuning version. And here are some results. We can see that after decoupled the retrieved information from the input task, especially when we put more document into the large language model, we can achieve much better performance than doing the naive RAG with the fine-tuning process. And the advantage would be larger when we put more put more documents here. The more document we put, the better improvement we get. And comparing the naive baseline, the vanilla RAG with our decoupled RAG in terms of efficiency analysis, we find that first, theoretically, for the vanilla RAG, the knowledge encoding time, the time it needs to encode those documents, grows quadratically with the number of documents, which is n here. We can see that the complexity grows quadratically with the number of n we have here. But after we separate the encoding of each document, the knowledge encoding time grows linearly with the number of documents we have. And also, we can do this whole process offline without taking the time for online inference. And so here are more experiment results. If we put more documents, which is the knowledge entry here, if we put more documents into our decoupled RAG pipeline, the offline decoupled RAG pipeline, the online inference time increase very little in terms of both the TFLOPs and the times. And if we use the naive RAG, which is this green line, the time it needed for inference increased very quickly based on the number of documents we put into it. And we also compared the decoupled RAG without offline knowledge encoding with the vanilla RAG. And we can also see that even without knowledge encoding offline, decoupled RAG still has some efficiency advantage comparing to vanilla RAG, because vanilla RAG encode all documents together, but decoupled RAG encode each document separately. Okay, so that's basically for the first part. Are there any questions? If not, I will just go ahead.
Did you see something popped up? Oops, it's disappeared. Did you see that before it disappeared? There's nothing in the chat?
Oh, yeah. So there's a question about, does the KV cache and cross attention happen at every layer of LLM? Yeah, actually, that's a very good question. So we actually did some experiment with this. Initially, we put the KV cache to all the internal layer of large language model, and it works pretty well. But later, we find that if we reduce the number of layers we put, it also produce reasonably good result. Then it's hard to say what exactly is good to, well, it's hard to decide how many layers you need to put into the large language model. For us, I can't remember the detail of the paper, but if I remember correctly, we initially just put it into all layers of large language model. Yeah, but I think there are experiments showing that if you put it into the initial 5 or a couple of layers, it also works pretty well. Yeah. Okay, thank you.
Oops, so
yeah, there are another question on what did, sorry.
No, you go ahead.
Yeah, so the question is,
Screen,
yeah.
so.
The question is on what data set did you train cross-attention parameters? Does it work outside the training data set? Yeah, that's a very good question. Actually, we did that on Wikipedia, if I remember correctly, right? So the way we do it is basically given a prefix, and we retrieve some kind of similar or relevant chunks from Wikipedia and let the model to predict the next couple of tokens after that prefix. So in this way, we don't need to actually, well, we can use any corpus to do the task, but the question is whether the model would work outside of the training dataset. I think for the dataset we task, most of them, I think many of them retrieve document from Wikipedia. And we haven't dig into the detail of it because we haven't done this OOD experiment, particularly for this text. But I guess as long as you have a reasonably large training corpus like Wikipedia, it should be able to generalize quite well. And also for the training part of cross attention, actually the number of parameters we have there is not a large number. Most of the work has already been done by the large language model, which is frozen when we use it. So I think if we don't have a lot of parameters, it should be less, it should be less likely that the model will overfit to the training data. Yeah. Thank you. Okay, so I will go ahead.
Yes, please.
Okay, so that's pretty much about the, thank you. That's pretty much about the first part. And the second work we have done on this direction is parametric retrieval augmented generation, which is a work I'm personally quite excited about. So let's look back at the very foundation structure of large language model. We all know that large language model is built from transformers, right? If we look at transformers, there are two important parts of transformer that have parameters. The first part is attention. So the attention layer has a lot of parameters to guide the model to interpret dynamic context. And it's very good at taking external knowledge into the model and use it to do generation. It's very good at dealing with dynamic context. And the way we inject our retrieval knowledge into large language model in the previous work is actually doing this through attention layer, right? So we are using cross attention. We're just adding things into this attention layer to let the model use the information from the external document. But the problem is attention layer is not the only place where large language models store their internal knowledge and internal information. Another part of the transformer is the feed-forward network. Actually, there are many studies showing that the feed-forward networks are probably more important for large language model to store its internal knowledge, to store its internal information, etc. And they are basically the foundation for the reasoning ability of large language model. It's kind of like human brain. So if you inject external documents or knowledge through attention layer, it's basically a student doing an exam with a textbook beside him. So he or she can read the textbook while finishing the exam. But if you put the knowledge into the feed-forward network part of the large language model, it's basically like a student study a lot of textbook before he or she take the exam, and he or she has mastered all the knowledge in those books. Then he take the exam, so he can use those knowledge right from their mind to do all the reasoning, to all the complicated job. And apparently, knowledge in these feed-forward networks can help large language model to do better job and to do better reasoning. So if we look at the existing RAG pipeline, just as what we have discussed previously, most of the existing RAG pipeline just do knowledge injection with in-context learning. So basically, they just put all the retrieved document into the prompt of the large language model and use the attention layer of the large language model to take the external information, to do the reasoning, and then generate the final answers. That's almost the same for all existing RAG pipeline. But we know that in-context learning has many disadvantages. First, we have talked about the context lens problem in the previous part of this talk. And the context lens problem would lead to computation overhead, slower generation, longer inference time, etc. But another very important disadvantage of this in-context knowledge injection is that it has a structural limitation. That is, large language model may never use external knowledge as good as their internal knowledge. Just like human, if we do exam using textbook without reading the textbook in advance, probably we can finish the exam, but we may not finish it very good, right? We may not get a very high score. But if we have already mastered all the knowledge in that textbook before we take the exam, memorizing it and learning it, putting it into our mind, then we do the exam, we can get much higher score. So the question is, instead of input context, can we inject retrieved knowledge directly into large language models parameter, particularly the feed-forward network part? So here is the traditional RAG pipeline. We have a user input. We retrieve a couple of documents, build it into the prompt, and then let the large language model to take the prompt, use the attention, etc., to finally generate the response. And in contrast to this, what we propose is a parametric RAG pipeline. We use user's input, retrieve some document, convert each document into some kind of parameter of large language model, and we then merge the parameters of the retrieved documents all together to create a merged document representation, injected this part of the parameter directly into the feed-forward network layer, the FFN layers of large language model, so that the large language model can use this external knowledge in the same way as it used the internal knowledge. So this is our goal in parametric RAG. And let's talk about how to do this. There are two parts of this parametric RAG framework. The first part is offline document parameterization. Because we want to inject the document directly into the internal parameters of large language model, we have to convert the document into parameters before we do this injection. And the second part of this framework is online inference. How do we actually use the parameterized representation of document in this RAG pipeline for large language model? For the first part, the offline encoding part, we need to do this, we propose to do this offline encoding with two steps. The first step is document augmentation, and the second step is parametric document encoding. So I will go through this part one by one. First, about the document augmentation. Basically, in this part, we want to teach LLM about the knowledge in this document. For example, when we want to learn about knowledge in a textbook, we probably will find some exercise, or probably will generate some question about the textbook and then memorize the textbook, try to answer those questions by ourselves, and etc. So to mimic this process, we use two types of document augmentation method to generate the training data to build this document parameterized representation. The first one is document rewriting. We just generated rewritten versions of the documents, but we want the rewritten version to maintain the factual consistency. So basically they are the same document, but writing in a different way. And the second part is the QA pair generation. We just generated multiple QA pairs based on the content of the document and teach large language model to answer those questions during this process. Basically, in this way, for each document, we build a tiny training data set for the construction of the parameterized representation of this document. So this is the document augmentation part. And the second part is the parametric document encoding. So we have the tiny training set for this document. Then we need to find a way to build the parametric representation of this document. The way we do it is to use pluggable parameter efficient fine-tuning components like LoRa. I think LoRa is quite a famous method to do this parametric efficient fine-tuning, right? It's basically just put a small part of the parameter into the feed-forward network of large language model. So we have the tiny data set for each document we get from the previous step, and we then use this to train a very small LoRa for each document. And after training this LoRa, we just treat the LoRa weight. So this LoRa part, the LoRa component, as the parametric representation of that document. For this training part, we just need to do next token prediction based on the tiny training data set. And we can do it just for one epoch because one document is not a lot of data. So doing it for one epoch, it would be enough. Okay, so that's the offline document parameterization process. The second step is the inference, or the second part of the framework is the inference procedure. So we have already converted document into the a parametric representation that can be used for large language model. Now we want to use that for actual generation. The way we do this is to do RAG through a 3-step process called retrieval, update, and generation. For the retrieval part, we just use whatever retrieval system we have to retrieve the top K relevant document for this user input for this part. And after we retrieve the document, we just find the parametric representation of this document, which can be computed offline. And we just merge all these parameters together in this update part and put it into the large language model. After we put all those documents into large language model, and we can do the generation just following the typical pipeline, put user input into it, and then do the generation. There are a couple of things I want to note it here. So for this whole process, the parametric representation can be built offline. And also when we put the document into large language model, we don't need to put it into context. We just directly put it into the parameters so that it won't increase the context length. Okay, so now about experiment. We have done a couple of experiments with some famous baselines like Flare and Dragon, and also a couple of large language model like Llama 3 and QWin. We also did experiment on a couple of benchmarks like these are typical question answering benchmark people are using for RAG today. And here are the big table for the results. It's a little bit heavy, but I will go through it one by one. The first observation we have is that this in-parameter knowledge injection method actually works really well. So here, the DA RAG is the data augmentation version of RAG for a baseline. It's a little bit complicated. So what we do here is to use the naive RAG, but instead of just putting the document into it, we also put the document augmentation, the tiny training data set we have mentioned previously. We also put those things into the input context of the large language model. The reason why we build this baseline is to show that the advantage of in-parameter knowledge injection is not come from the document augmentation itself. So if you simply do the data augmentation for each document and put the augmented text into the context of large language model, it won't increase the performance of RAG. And actually, in most cases, it will hurt the performance of RAG because the context will become even longer. But if we do this way in parameter, like if we do this in parameter injection, the performance of our method like PRAG here usually are much better than the standard RAG baseline. Okay, another thing we find is that if we combine this parametric RAG with in-context RAG, it can achieve even better result. So here for this line, we combine both the in-context knowledge injection and the in-parameter knowledge injection method together. Basically just put the retrieve a document also into the prompt of this PRAG, it can get even better performance comparing to both the standard RAG and the parametric RAG. So it means that the parametric RAG is in parallel, or I should say, it doesn't affect the effectiveness of in-context RAG. So basically, there are two methods that have different advantages. In terms of efficiency, we have done a couple of analyses. First, for the theoretical part, we have done a theoretical analysis on both the offline parametric and offline document parametric representation learning part and the online inference cost of this parametric RAG. So for offline cost, the main costs come from the document augmentation and the LoRa training part. So here is the overall complexity of this process. And because we only train this LoRa for like one epoch for each document, it's basically approximately outputting like 12 multiplied by the length of the document tokens for large language model. So the cost is basically the same with letting a large language model to generate it like 12 multiplied with the length of the document. If the documents have only 10 tokens, the whole training process of this parametric representation is just outputting about 120 tokens, stuff like that. And for the online cost, is basically just the input instructions, because we don't have any context overhead. We don't put document into the context. So the online costs are significantly lower than the traditional RAG. And here are some experiment results. So if we use this parametric RAG, the inference time of the whole process would drop about 30% to 39% to 36%, which is much faster than the standard RAG. And this doesn't count about the time we updated them. If you remember, we have to put the model parameter into the model, right? So this small number means the time we need to put the LoRa parameters into the large language model. This time also have a tiny overhead. And because our code is not optimized for this, it takes quite a long time to load parameters into GPU. But you can definitely do more engineering trick to make this time much quicker or much faster. So in the end, the overall inference time of parametric RAG is much lower than the standard in-context RAG. Okay, so that's basically about all the work in second part. And I don't have a much slides, so I will just go through it and finish all. And about the future work, we know that information retrieval has changed quite a lot in the past like 60 years. Previously, we have been working on library stuff like retrieving the textual document. And also in about 1990s or 2000s, we started working on web pages and do web search engines, which was a huge success. And starting from 2000, probably just 2022, because of the rise of large language model, we are entering an era of generative AI. So the question is, what information retrieval can do, or what generative AI can do for information retrieval in the future? And here are some thoughts I have. It may not be correct. When I look at large language model and information retrieval system we have, I remember many things we have learned from previous class. For example, we have learned about computer architecture in our computer architecture class, right? So in computer architecture, we have RAM, hard drive, and CPUs. To me, I think large language model looks like the CPU of artificial intelligence system. And information retrieval system is like the RAM or hard drive of artificial intelligence system. You can't say that CPU is more important than hard drives. And also, if you don't have CPU, just hard drive, it also won't work. And similar thing you can observe is human brain. So actually human brain can be split into a couple of parts. Some parts are in charge of perception, some part are in charge of thinking, and some part are in charge of memory. For the whole brain to work, these parts must collaborate with each other in a very efficient way to make the whole brain work for a different kind of task, right? And large language model is like the part in charge of thinking, and traditional information retrieval is like the part in charge of memory stuff and manage the information we have in the memory. So I guess in the future, for the building of next generation of AI, information retrieval system, traditional information retrieval system will combine with large language model to do more complicated tasks. And that's what we have been hoping to do in, I think, for many years. Previously, we can only do simple documents retrieval and like web page retrieval, mostly, well, not mostly. I think a part of the reason is because we don't have a very powerful tool that can actually help us to use the retrieval information for the downstream information task of the user. But now we have it. Large language model can help us do that. So in this way, for the next generation of AI system or the next generation of information retrieval system, we want to use information to help user to finish their complicated downstream information task directly. And that require large language model and the retrieval system to collaborate with each other in more efficient and more effective way. There are many questions related to this, like how to do adaptive reasoning with retrieval generation, how to do this efficient information or knowledge injection, etc. And yeah, there are many ongoing work in this direction. And I think this could be a very fruitful direction in the future. Okay, that's all for my talk. Yeah, a little bit over time, but thank you for listening. Yeah.
Thank you. Thank you, Qingyao. Are there any, we've got a little time for questions though. So is there any questions? I actually figured out how to see the chat. Any questions locally? Well, I'll ask one while people are absorbing all of that. In the second part of the talk, you created a sort of a little LoRa model for every document, the delta W per document. And then you combine them by just adding them together. Is that, I mean, it works. It's like, it's obviously not a terrible thing to do, but is it the case that they're truly independent, or should you somehow, would you get better results if you could somehow blend them in a more principled way, let's say?
Yeah, thank you for the question. Yeah, it's actually a very good question. The funny thing is, like, we did try a lot of things to combine those LoRa, and the leading author of this paper, Wei-Hang Su, he has tried like 4 or 5 type of way to combine this LoRa, and in the end, we find that all those more complicated way, they didn't work for this text. Using this adding process, we just simply plot them together, give the best result overall. And we are working on this part because I think there might be some reason behind this phenomenon, probably due to the way we build LoRa. And one of our current work is to try to find some theoretical foundation for this process, try to see why this adding process can give you the best performance. And perhaps if we can have more or better foundation theoretical understanding of this problem, we can find some other method better than LoRa to do this parametric representation for a document. Yeah.
Great, thank you. Any questions? Oh, it's too early in the morning for people here.
Yeah.
Okay, well, if that's it, then we can thank Qingyao again. So thank you so much, Qingyao. Once again.
Thank you.
No, he already did.
Okay. Okay. So I guess that's it for today. Thanks again so much. I think you're going to be meeting with the faculty. We're going to have some Zoom chat in a few weeks or something like that because of beginning of spring break and things.
Yeah.
We're busy. So we look forward to seeing you then. Thanks again so much for the talk, and have a good night.
Yeah, thank you.